Welcome back, ladies and gentlemen. In this video, we will talk about applying Kirchhoff's laws in combination circuits. Okay, first of all, just a little recap. On your screen is a parallel circuit. This circuit is supplied with a total voltage of 60 volts, and then it runs through 3 separate resistors in a parallel configuration. So just a reminder, our solving circuits toolbox entails using Ohm's law. So the current through a resistor is the voltage divided by the resistance. We're also going to use Kirchhoff's current law, where the current into has to be equal to the current out of a junction. Okay, and these points like here, that's a junction. Okay, and Kirchhoff's voltage law, which says that the voltage gains through a battery has to be equal to the voltage drops around a loop. So if we think about the bank analogy, if we're given $60 as we leave this battery, and here's the long side of the battery, which would be positive, and our negative is the other one. So I'm always going to draw conventional current, or think about my loop going in conventional current. So a loop would be like so to get back to the battery, and it means that the voltage gains through the battery has to be equal to the voltage drops, in this case through V1. Okay, so I'll move that out of the way. There is a busy slide warning in the top corner. There will be a lot going on with this question, so please draw this. The table that's there will be for us to record all of the values that we are looking for. Okay, so the first thing I'm going to do is I'm going to apply Kirchhoff's voltage law and just redraw that loop that I first drew. Okay, if that is our loop, our gain through that loop through the battery is 60 volts. That means that our voltage drop through the resistor or that load has to also be 60 volts. Okay, so I'm going to put 60 over in the table. Okay, if I erase that loop and then draw a different path for electrons to follow, here though, let's put them through resistor number 2. Again, resistor number 2, the voltage drop through that resistor will also be 60 volts. And you guessed it, if we were to erase that and draw another loop through resistor 3, the voltage drop through resistor 3 would be 60 volts. Okay, so next, I'm going to look at finding the current in resistor 1, just to use each of our different tools in our toolbox. So the current through resistor 1 will be the current that's shown. Okay, we're going to use Ohm's law to solve that. So V over R, and as long as our subscripts are all the same, the current through resistor 1 is equal to the voltage drop across resistor 1 divided by the resistance of resistor 1. We should get our correct number here. Voltage drop through resistor 1 is 60. Divide that by our resistance of 17 ohms. If we plug and chug that, we get 3.5 amps. So 3.5 amps is our current through resistor 1. Okay, we could do the same thing in branch number 2. Just using our V2 divided by our R2, which would give us 5 amps through resistor number 2. Now I could do that again for resistor number 3, but I'm going to hold off just so that we can use the Kirchhoff's current law in this question. Okay, so what we'll often be asked for is what is the total current through the battery and the equivalent resistance of the circuit. So to do that, I need to, I use the word collapse the circuit. I need to convert the circuit that's on our screen to something that looks much simpler, like so. I'm going to change or collapse all 3 of those resistors into one and call that our equivalent resistor, okay, or total resistance. Those 2 words are used interchangeably. Okay, because this is a parallel circuit, I'm going to use the formula for parallel circuits, which is just 1 over each resistor, add those together. So this is where the 1 over x button on your calculator, or the x to the -1 button on your calculator, will come in handy. Okay, if I plug in some numbers here, R1 is 17, 1 over R2 plus 1 over R3. Okay, then I can go on my calculator and hit 17, 1 over x, plus 12, 1 over x, plus 11, 1 over x, equals 0.233. Okay, and then I need to hit 1 over x again to flip our EQ, or get our EQ in the numerator, and we should find that our total, or our equivalent resistance for this circuit, is 4.29 ohms. Okay, so let's number go up here. Okay, which makes sense. As we add loads or resistors in parallel, it decreases the overall resistance. So that makes sense that value is at a 4.29. Okay, next we'll find our total current in this thing. So I'm looking now at our new circuit that we built. So our total current will just be our total voltage divided by our equivalent resistance, which we can find by doing 60, which is our supply voltage, divided by our equivalent resistance, and we should get a current of 13.9 amps in this circuit. Okay, so that number will go up here, 13.9. Okay, and then lastly, just to use Kirchhoff's current law, if I know that coming around, just going to get rid of this line here, coming around out of the battery, the amount of current that's flowing into this junction point is 13.9 amps, and then some current is flowing out to the left through R1, that is 3.5. There is some current that's going out to R2, and then there's also some current going out to resistor number 3. The current going through resistor number 2 is 5 amps. So these three numbers, or these three currents, are all coming out of that junction point. Those three numbers added together has to be 13.9 amps. Okay, so if we do a little subtraction, 13.9, subtract the two currents that we know, we should find that the current in resistor number 3 is 5.5 amps. Okay, and that question's done. You'll see it's quite a bit of work, right? Quite a bit of work and some a lot of reasoning to try and get to values for all of the things that we're looking for. Okay, so next we're going to use those toolbox, or that toolbox, to solve something a little more difficult. So in the last video, we talked about the goal being to solve circuit puzzles, and to solve circuit puzzles, that means to find the current in each branch, okay, find the voltage, drop across each resistor, and find the resistance in each resistor, okay, and then as an extension, to find the power in each resistor by applying P equals IV. Okay, so what if we back that up? So on the screen, there's a big circuit and all of the values are given to you. So if we start this question off with what it might look like to start off, this would be the question started off where you're given a few values and then we are going to be tasked with finding the rest. Okay, so the next circuit on your screen, this is a combination circuit that we will solve. Please draw this, and if you're looking at this thing going, what is going on? There's a lot of resistors. Where do I even get started? You're a little frustrated. You're like, what? Dietrich, come on. I don't know what to do here. Don't worry. We're going to make a little plan and we're going to solve this thing in many slides. It'll take a little bit of work, but we will get there. Okay, so can you please draw this circuit? I'm also going to talk about the steps. So our steps to solving these circuit puzzles are, we're going to need to find the total or equivalent resistance for the circuit. That means that, yes, that big combination circuit on your screen will end up looking like this. Okay, we are going to collapse that circuit into something that looks like this to find the equivalent resistance, and then also the total current going through the battery. Okay, we're going to find the total current for the circuit. And again, that is the current going through the battery, Okay, and then we're going to use Kirchhoff's laws and Ohm's law while we, what I call, expand the circuit. Okay, so there'll be lots of analysis going on here. This is the start of our electrical engineering careers, looking at how current, voltage, and resistance is affected in a bigger combination circuit. Okay. Okay. Added to the circuit on the screen, can you please make a table for yourself? We are going to be finding all kinds of values, and a lot of these values are given to us off the hop here. So we already know what our total voltage is that's given to us. Okay, so I'll put our 48 volts in there. Okay, we also know what our resistance is for all of our resistors. It's 40. R2 is 24. R3 is 60. And R4 is 90. Of course, the units for each of those is ohms. Okay. Okay, so even before I go forward, we do want to find our equivalent resistance, but I'm just going to do a quick analysis and just do a little thinking of this thing. So using Kirchhoff's laws, the voltage law specifically, I know that as I go around a loop, my voltage gains has to be equal to the voltage drop. So I'm going to look at this first loop, and again, our positive side of the battery is indicated with the long line on the battery. Our negative is the short line, and I'm always going to think of current coming out of the positive side, which we call conventional current. Of course, we know now that electrons actually flow from the negative terminal, but conventional current is still a pretty common standard that's used to talk about the direction of current. Okay, so I know that with Kirchhoff's voltage law that around this loop, my voltage gain has to be equal to the voltage drop. So here our voltage gain through a battery is 48 volts. That means our voltage drop through resistor number 1 has to also be 48 volts. So I'm going to go and put that number in here. Okay, if I have two things in a row in this table, I could find the third. So this table is set up with V, I, and R. And I did that because it's kind of how Ohm's law works, right? V is equal to IR. So if I want to find the current flowing in branch number 1, I can take our voltage drop across resistor 1. I can divide that by the resistance of resistance 1, and then we can plug and chug to get some numbers. And we know that our I current in branch number 1 will be 1.2 amps. Okay, so we'll add that value in here, 1.2 amps. Okay, and then we'll go on to our next part of this big question. Okay, so next, step 1 in our problem-solving approach here is to find the total or equivalent resistance for the circuit. So in other words, collapse the circuit. So our first step is to analyze what are some resistors that we can combine using our rules for series and parallel circuits. So looking at this thing, the first thing I'm going to do is I'm going to collapse those two parallel resistors, and I'm going to turn them into resistor 5. And I'm just calling it resistor 5 so we have something to talk about. So, So resistor 5 using our parallel circuit setup, 1 over R5 will be equal to 1 over 60 and 1 over 90. So I'll give us a little more space here. So 1 over R5 will be 1 over 60 plus 1 over 90. Okay, when you're plugging and chugging, you should have your 1 over R5 is equal to 0.027 repeated. Okay, and then if we flip that again, we'll end up with R5 is equal to 36 ohms. Okay, please try that calculation on your calculator. Make sure that you're getting the same values as me. If our calculator, if we're using our calculator incorrectly, it'll throw this question off pretty quickly. So please do try that, those steps on your calculator. Make sure that we're getting the same numbers. Okay. Okay. Next, so I put our values into our table. Okay, so now we're going to keep going here, and we have our R5 that we just found. We're not going to put that in our table because not an actual resistor that we're being asked for. But the next step we'll do is to combine those two series circuits and change them into an R6. So R6 is just going to be the sum of R2 and R5. Okay, if we plug some numbers in here, okay, we'll get that our R6 is 60 ohms. Okay, and then we are going to keep going. We'll keep going here and get all the way to a point where we have just our equivalent or our total resistance. So finding RT in this case will be 1 over 40 plus 1 over 60. Again, that's our parallel circuits setup. So our 1 over RT value here will be 0.0416 repeated. And if we flip that, we should end up with our total resistance of 24 ohms. Okay, so if our total resistance for this thing is 24 ohms, we can then solve for our total current by taking our voltage, dividing it by resistance. This is just Ohm's law. So the total amount of current that is flowing through this battery is going to be 2.0 amps. Okay, so this is a big one. We just found two numbers. Okay, we'll put those into our table. Okay, and then move forward from there. Okay, so we've added those numbers into our table. And again, this is a busy slide warning because we get into trying to solve things here that or we're applying our three rules in a few different ways here. We're applying applying all three of those laws. Okay, so our next step here, the next thing that I'm going to do is just kind of draw a couple things on here. I'm going to draw my current coming out of this junction point being 2.0, or sorry, into this junction point is 2.0. That is our total current for this circuit. We've already found that the current then leaving this junction is I1, or 1.2 amps. So the current that is heading off or also leaving that junction point has to add up to, I'm going to call that I2 because this is the current that will flow through our second resistor. So this I2 has to be 0.8 amps. Okay, and again, that is just current into is going to be equal to the current out of a junction point. Okay, so our I2 is 0.8 amps. Okay, then in that second row, we can find our V2 using Ohm's law. I2 is 0.8, R2 is 24, and we'll find that the voltage drop across resistor number 2 is 19.2 volts. Okay, so V2 is 19.2. Okay. Okay, so next I'm going to analyze this thing again, and I'm going to use Kirchhoff's loop rule or voltage rule. So I'm going to think about a loop as being one that looks kind of like so. Apologize for all the lines. Again, it's a busy slide warning. Let's go down this way, back to our battery. And again, if we think of this as a money analogy, we know that our V gains through the battery has to be equal to our V drops around a loop. So in the loop that I've drawn, our gain through the battery is 48 volts, and that has to be equal to the drops. Well, in the line that we've drawn, we go through resistor number 2, where we drop 19.2 volts, and then we also have to add to that the voltage drop across resistor number 3. Okay, and if we plug and chug for finding the voltage drop across resistor 3, we'll get 28.8 volts. Okay, and then we can also analyze this and think, well, that voltage drop has to be the same through resistor number 4, because I'm just going to redraw another loop where it's the same thing, where I'm going through resistor 4, and I could do that same calculation again, but I'm not going to show the calculation twice, but we know that the voltage drops through resistor number 3 and resistor number 4 are 28.8 volts. Okay, and then of course using our Ohm's law to find current number 3. Okay, I'm using items from resistor 3 line, okay, where we have our voltage drop through resistor 3 is 28.8, okay, divided by our resistance of 60 ohms. We'll find that our current in branch number 3 is 0.48. Okay, we'll put that number in here, 0.48. We're almost there. We just have one more to solve. Okay. Lastly, if we think of our junction rule, so again, where we have, in this case, I'm going to look at, and sorry guys, I think I'm just going to skip to another slide here and just show this as current coming into this junction. That is our current 2, or I2. Then we will have current leaving the junction. I'm going to call that I3 and I4. Okay, so using our current in is equal to our current out, or Kirchhoff's current law, we can find that our current into the junction is 0.8 amps. That's just, maybe I'll even write out here, guys. I2 is the current going into. The current leaving that junction is I3 plus I4. Okay, we know that our current 3 is, we just found that our current 3 is 0.48 amps plus current 4. Okay, and we can do a small bit of math here to find that our current through branch number 4 is going to be 0.32 amps. Okay. Okay, so I would call that a monster question. There's a lot going on. Lots going on, but just we just have to keep in mind that our analysis of it really boils down to using 3 tools, being Ohm's law and Kirchhoff's current law and voltage law, and then just working to find values for each thing that we are looking for. Okay, so there's just that table totally completed, and then give yourselves a pat on the back, because that's a big question. Okay, that's there's a whole lot going on there. Okay, so nice work. Next, I have gone and found, this is just a complex circuit challenge on the internet. I'm going to zoom in on this a little bit. If I zoom in on this a little bit, we have a very complex circuit. We've got 120 volts supply voltage. Okay, we know all of our resistor values. R1 is 10, R2 is 12, R3 is 6, R4 is 10, R5 is 5, and R6 is 2. And of course, those are all ohms. Okay, so on this question, she has a mark out of 21. There are 21 things to find for this question. 7 of them you already know. So what I'm going to ask that you do is pause the video here. Okay, I'd like you to draw this question, work through it. The next slide that I'm going to show are answers. So what I would like you to do is work through this question honestly, and I'd like you to just tell me how many answers did you get correct. Okay, if you have nothing else to add, if you're totally stumped, you should still be putting a 7 down. You got 7 blanks out of 21 because there are 7 things given to you. Okay, so Can you find the other thing or the other values on the screen? This is a super hard question. So give it a try, see what you come up with. Your assignment is going to be a resistor assignment that deals with 5 questions with a bunch of different circuit setups. So give those a try. But let me back up and just pause here. Please pause the video, give this question a try, write out your answers, and when we resume, you can check your answers and just let me know how many out of 21 did you get. Okay, there is my complete solutions for this one. Again, just tell me how many of 21 did you get? You should have at least 7. Did you find more? Let me know. Okay, your resistor assignment, folks, is posted with this video. Thanks, and we'll see you again soon.